Long ISP Bluetooth Device Finder.
Alright, so currently it says we need to turn left. Right now the current heading is around 180 plus, whereas the heading we need to be is 45 degrees, 45.95, and it's also oscillating between greater than 7 meters and 3 to 7 meters the most. So we're probably around 7 meters away from the actual phone. So as it says, let's turn around left and let's see what happens. Okay, so we can see that the second heading changing. Okay, it says straight now. Okay, so let's do that. And let's move straight. As it says, we are getting some interference. We can see that it now says around the 3 to 7 range, and there is some 1 to 3 range as well, so we're probably getting closer and closer. So let's keep going straight, getting a good look at what's happening. And then we're getting straight. Oh, now we only see the 1 to 3 and less than 1 range, so we're definitely much closer. So let's keep going. Now, okay, so now we're in the less than 1 range. Most of it is in the less than 1. You can see that it's oscillating between straight and near, so it's definitely straight. So if we were to look around, there's the phone right there.
First of all, what is Bluetooth? Bluetooth is a short-range wireless communication standard that enables devices to exchange data without physical connections, typically over distances ranging from 10 meters to 100 meters, depending on the device's Bluetooth class. Bluetooth operates on the 2.4 GHz ISM, industrial, scientific, and medical band, which is a crowded frequency band shared by other wireless technologies like Wi-Fi and Zigbee. To avoid interference, Bluetooth uses a technique called frequency hopping spread spectrum (FHSS). This means Bluetooth devices rapidly switch between 79 different frequency channels within the 2.4 GHz band, reducing the chance of interference from other devices operating on the same frequency range, such as Wi-Fi. Bluetooth works by transmitting data in small packets, managed by the baseband component, which ensures accurate transmission to the correct device. The Link Manager Protocol (LMP) handles connection tasks like pairing, encryption, and maintaining the communication link. Once connected, devices use Bluetooth profiles, example A2DP for audio streaming, to send and receive data. The Bluetooth device is initially connected through a function that retrieves its MAC address, which is a unique identifier for the Bluetooth device, using central address and prints it into the serial monitor. This step provides a way to verify which Bluetooth device is currently connected. However, the program needs to ensure it's tracking the intended device, in this case an iPhone. To do this, it compares the MAC address of the connected device against the target address specified in target MAC address. If the addresses don't match, the program immediately disconnects from the device using central.disconnect. Note that for iPhones, they have their MAC addresses at random, so you have to go to settings and manually turn the random address off. Now, in terms of the calculating the distance part, it's based off of RSSI, and the equation to calculate it is based off of this. Pause the vid so that you can know what the variables all stand for. So it's through this that I'm able to calculate the distance between my device and iPhone. Note that some of the values may vary, but for an indoor environment, after lots of experimenting, these are my values. For the ESP32, you can retrieve the RSSI value by writing the command central.rssi. Now, in terms of the direction aspect, I use the QMC5888L magnetometer. It calculates the heading by using magnetic field readings from its x and y axes, which measure the horizontal and vertical magnetic field components, respectively. The heading is determined as the angle theta between the sensor's x-axis and the magnetic north, calculated using the A tan2YX function, and this function handles the angles quadrant correctly, ensuring the result falls between negative 180 degrees and 180 degrees. The angle is then converted from radians to degrees using the formula heading degrees equals theta times 180 over pi. To standardize the result within the range 0 to 360, negative angles are normalized by adding 360 degrees. For calibration, these were the numbers I had gotten, but it is best to do it yourself so it is more accurate. Based on the value of relative direction, the program determines whether the user needs to turn right, left, or stay straight. If the relative direction is greater than 35 degrees, which is like an offset, it sets turn direction to right, meaning the user should turn clockwise. If the relative direction is less than negative 35 degrees, it sets turn direction to left, meaning the user should turn counterclockwise. If the relative direction falls within the range of negative 35 to 35 degrees, the user is roughly aligned with the target, so turn direction is set to straight. Finally, everything is displayed in the OLED displays. The display info function updates the OLED screen by clearing the buffer, setting a readable font, and displaying key information. The distance to the target, example less than 1 meter, 1 to 3 meters, etc. The current magnetic heading, the target heading, and directional guidance, so like right, left, straight. Finally, U8G2.send buffer transfers the data to the display, providing continuous updates to help the user align with the target device. Thanks for watching.